Welcome everybody back. It's my pleasure to introduce our next speaker, Professor Christoph Lampert from the Institute of Science and Technology in Austria. I have two parts of my introduction. One is more formal and the other one is a little bit informal. So the formal introduction goes like this. Christopher received his PhD in mathematics in 2003 from the Bonn University. Then he joined above mentioned Institute of Science and Technology in 2010 as assistant professor and later as a professor. He's actually leading a research group of machine learning and computer vision. I was made aware that the sequence is very important. There is an emphasis on machine learning. Also, Christoph has his research and his group research has actually received a number of various national and international recognitions. And I think computer vision people like myself would appreciate the fact that Christoph had one of his papers as the best paper in CVPR conference, a very famous conference in computer vision field. Also, he has been awarded European Research Council grants, starting grant, and also editor on a few very esteemed journals. So that is the formal part of my introduction. There is an informal bit of it. Christoph is a famous researcher, but we haven't met in person until today. But there was a student of mine who used to work in my research group, but for some reason preferred to do her PhD in, I don't know, for weird reasons, for the Institute of Science and Technology. And she came back from the visit where she met the local professors. And she said, look, I'm so excited. There is this person. Their H index is super high. They're full of great ideas, extremely friendly. I'm completely blown off. It's great. And since then, I knew when Jaak reached out and said, look, who should we reach out to ask for the ESSCaSS? I knew exactly that Christoph would be my this top priority person. And that's why I'm so honored and so glad that Christoph made it here to Estonia, especially after the COVID period. It's a big pleasure. Thank you very much for coming. The floor is all yours and the audience is also yours. So thank you very much.
That's not how it goes. Okay. What's the pointer? Ah, technology. Cool. So thank you for the nice introductions. Okay, let me start. The organizers told me that this is a very open summer school and not everybody has a machine learning background. So I decided to start with a very, slow, well, in a positive way, hopefully, introductory way. Can we have a quick show of hands who has actually or works on machine learning scientifically in master thesis, PhD or something like that, who wouldn't consider themselves a machine learning or artificial intelligence person? Okay, who wouldn't? Who hasn't heard of binary logic? Okay, good. Okay, so maybe some of you will be then bored in the beginning, although it sometimes helps also to see things from different perspectives. And maybe if you, in case you feel bored, you can, record the mistakes I make in the first hour or so, because then I can edit my slides accordingly. But I would like to start in a very different way, because I come to you from IST Austria, as we just heard. This is a research institute close to Vienna. And not everybody has heard of it, which is a pity. So let me start by 1 minute of advertisements. We are a public research institute funded by the Austrian government in 2009. We concentrate on basic research, curiosity-driven, so we're not solving problems so much as like trying to understand and develop methods. There's a strong focus on interdisciplinarity. It's not just computer science. It's kind of mixed between biology, physics, chemistry, now recently earth and climate sciences. And in case you've heard of the ELLIS network, we have a unit which will come up also in my third lecture, the more general one on tomorrow afternoon. We can grant PhD degrees, which is very useful. So we have a PhD program that follows the US style. People are paid well. And I'm telling you all of that because of course, we're hiring. So if you're interested in internships, those of you who don't have a PhD position yet, maybe you're interested in one, Or after the PhD, you're interested in a postdoc, or you want to be a big shot professor, just send me an email afterwards or visit my homepage for further information. Okay, that was the commercial break. Now let's start with the actual science. The schedule is mixed, is fit into this kind of subtopics. I will start with the general introduction to machine learning, as mentioned. I will then focus on the two other words in the title, which is robustness and fairness. And maybe these are more, I mean, they're not as mainstream, but I think still very relevant parts of machine learning, especially these days where machine learning systems are not just on the device of the researcher, but also in the general public. The second lecture will be about more specific topics of research that our group has worked on recently, which is certification of robustness and fairness and robustness for multi-source learning. And tomorrow there will be a more general lecture about how to do a good PhD, what does being a researcher mean, hopefully for like general audience as well. In the meantime, feel free to interrupt me anytime. I think the audience is small enough that, I mean, I can answer questions on the fly. If I go too fast or too slow, just let me know. Then we'll hopefully have a good experience. Let's start very general. Machine learning, artificial intelligence is all over the news. Of course, everybody who doesn't work on it still has heard about it recently. And typically, it's presented as this kind of high-flying, amazing, is going to rock the world topic, which you have to answer questions. Will humans be eradicated? Are AI systems already sentient these days? Will AI replace Tom Cruise? So these are questions as you will find them in the news regularly. This is not how I see artificial intelligence or machine learning. For me, machine learning is just a way of developing software. So like each of us hopefully know how to create a piece of software. Machine learning is just one way of doing that. So let's start with a very simple example. How does creating software work? In the classic process, if you want to solve any kind of problem using a computer, you would first formalize it. You would say like, oh, I would really like to have a function, let's call it sort, that takes as input an array of numbers, and it outputs an array of numbers, and it should have a certain functionality that might be given by a specification. So the output of this routine should be a permutation of the input, which you can write down mathematically to the computer. And the output should also be sorted in increasing order, which you can also write down as a mathematical formula. And then some smart software developer will sit down, come up with an algorithm. It will hopefully show that this algorithm does the right thing, formally or with verification techniques or anything. Then you implement this, hopefully without errors. And then you will have to check that you implemented this correctly by using some kind of test cases, if you do it right. So you will give it some inputs, check that the specifications are fulfilled on the output. So this should feel familiar to everybody who writes software. Now, some tasks are very hard to treat in that way. And here's an example task, recognizing voice commands. What we want is a subroutine that takes as input an audio signal and it outputs either start or stop, depending if the person said start or stop. That sounds reasonable, right? Every Alexa, smartphone, etc. device should be able to do that. But the problem is we don't have a specification what that actually means. We can express it in like high-level language, right? Everybody understands now what the task is, but the computer has no clue because we cannot formalize it on a mathematical level what it means for an audio signal to contain the word start. At least I don't. And this means if an ordinary person, like a software developer, sits down and tries to write a piece of software that takes an audio signal and turns it into start or stop, probably not going to make a lot of progress. So this is the observation that for certain tasks, software development just fails because we don't know what we really want. Machine learning enters here by saying, let's still create a function that recognizes inputs and outputs something else, but we don't need a specification that formally explains what we do, but instead, we're just giving it a bunch of examples of inputs and the correct outputs. So this is the classic called training set. And then we let machine learning do its thing, and it will output its own implementation of such a function. So it's a very lazy way of software development. We only give it examples of what we hope to achieve, and then the computer does the rest. Of course, if we don't have a specification, how do we know if the implementation that the computer gave us is correct or not, or how good is it actually? So what does correct mean in this purpose? And if we would be able to write down a function that says it's correctly doing this or that, if it fulfills certain criteria, then we would have a specification again, right? So what machine learning does instead, it specifies a loss function that tells you for every possible output the model could take, how bad is it to make a certain output, y prime here, if the correct output would have been y. And the simplest example that we can always think of is just predicting discrete outcomes like start or stop. And then the loss function would be just checking if the output is equal to the intended output. So that would be the 0-1 loss function that hopefully most of you have seen. If you want to predict real numbers, you put something like squared loss. How far away is my prediction from the true? So these are things that you can compute even without knowing what the true answer is. You're just saying, if I have two answers, I can compare them. And with this, we can now decide, well, which model should the algorithm actually output? Well, we go through all the training examples. That was the xi, yi from the training set that we were given. We compute the output of our model f for every input compared to our output for the specific example, compare them with the loss function that gives us a number for each example. We sum all of these numbers, and then we try to find the model that minimizes this number. So that just means we try to find the model that makes the smallest number of mistakes given the training data that we've given it. So this is a very intuitive thing. Like, if you have to choose one model, choose one that makes few mistakes. It kind of makes sense. Now, this is abstract, right? So how would that work in a computer? Well, you need to choose some kind of class of models that you search over. And I mean, as we've heard a lot of times already, neural networks are currently the fashion to do that. So a neural network is just a large class of parameterized functions, meaning it's a very large class of possible functions that could be represented with this network. And you can index all of them with some parameter vectors. In this case, your network is a concatenation of little steps. So, and every step is just some linear transformation of your data, or technically an affine transformation, followed by some nonlinearity, like throwing away the negatives, keeping only the positive values. So each operation, it starts at any input you give it. It does this linear transformation followed by some nonlinearity. Then on the output of that, you do another linear nonlinearity, another linear and nonlinearity, and so on. And in pictures, we typically, where's my pointer? Sorry, not used to this yet. There we are. And we typically draw this as like a cascade of little circles. So you start somewhere at the bottom, then you take your data and you transform it to the next layer, you transform it to the next layer. Each of these is a simple routine that can easily be implemented, and in the end you end up with some values, which is your output. And each possible model of this architecture can be described by just giving the coefficients of the corresponding linear transformation. So these are weight matrices. So we will always have some kind of weight matrix W and additional additive term B, which is called the bias term. And if we know all of these matrices and the corresponding vectors, the model is completely described. That also means we can search over all possible models by just searching over all of these weight matrices. And that means the optimization problem up here has turned into some kind of numeric optimization, and then we can use any optimization method we want, and the typical one is a form of stochastic gradient descent that we've seen in a lot of the previous talks already. So this is all there is. Now you have, recovered what's called deep learning in this kind of more intuitive or more flashy name. Okay, so that sums up machine learning on one single slide. You have an input, for example, audio signals. You have outputs, for example, a discrete set of labels you want to achieve. You're looking for a function that turns the input into the outputs. To find this function with machine learning, we have to specify like what is a good answer, what is a bad answer. That's the loss function. We need a training set, and we'll talk about that mostly later. And we have to choose a certain set of models that we can even search over, parameterized by some numbers that the computers can understand. We use a form of gradient descent to minimize the amount of mistakes that it makes. That's called the training phase, and we are done. And this is basically what's happening in the machine learning community 24/7. Everybody takes the data, takes a model, runs gradient descent, and then says, well, now I've trained my model. But there's a lot of questions still open, and one of them is like, is that a good idea, right? I mean, will it work? Will it work not just on the training set, but will it also work in the future? And what do we mean by the future? because nobody talked about the future yet, right? We only talked about the data set. So for that, let me give you one excursus on probabilities. Luckily, we've heard a lot about probabilities already. So for me, probabilities are the most important tool that machine learning has to offer, so it's worth giving them their own slide. Based on the observation that most quantities we see in daily life are not fully deterministic, so there's true randomness, like quantum effects, which apparently are stochastic. There's uncertainty due to measurement error. There's incomplete knowledge, as has been discussed earlier today. There's insufficient representation. So the information is there, we just cannot access it because it's not expressed in a form we understand. And these are often indistinguishable from each other. Although Eike's lecture, of course, told you how to distinguish a little bit of these, but we're not going to need this. So for us, the message is that probability theory allows us to deal with all of them in a consistent way. We don't have to have to care for the rest of this lecture if something is unknown for this reason or unclear for the other reason. Probability theory will allow us to just handle all of these as probability distributions. Okay, so now, how good is our machine learning model, what we trained? Of course, we don't know what the future will bring to us, right? So we need to make some assumptions. What does it mean for a model to work well in the future if we want to understand how to create good models? And probabilities help us in that respect because we don't know what the next input data will be. Well, we have to make it a random variable then. There's a set of all possible inputs to the system, like say all images, all audio effects, something like that. And we just assume that there is some kind of probability to see any of these. And something that has 0 probability is just not possible to happen. Everything else will have some probability to be the next input to the system. Similarly, we don't know what the correct output would be, right? Because otherwise we would be done. But we assume that there is at least some relation between the inputs and output that we can capture in a probability distribution. So we introduce a random variable for the output y, and then for every possible x, different outputs might be possibly correct, and which one is how likely is given by the conditional probability of the output given the input. This can also be deterministic, right? Probabilistic doesn't mean it can't be deterministic. That would be a delta peak, but it could also have uncertainty of any kind. Important to note, we don't pretend that we know these, right? It's not that we make an assumption the world's a Gaussian, but we just assume there is some kind of probabilistic effect happening. And the only way we can access it is through the training data. Okay, so we have inputs and outputs. We have a set of models. Everything is set in order to learn a model. So what do we want from a model, really? Well, it should work in the future, as I said. And that means it should have, if you give it new data, it should predict it as correctly as possible, which we can measure by the expected value of the loss, which is also called the risk. So for the sake of this talk, we will only look at expected value of the loss for now and say, like, any new instance, it should be as good as possible on average. Of course, we can't compute this because we don't know what the future will bring, right? But statistical learning theory has come up with ways of establishing conditions on the data set, on the set of possible models, so that we can prove statements about this. And this means we have some guarantees. It's not just what some people have to do at the moment, which is train and then see if it works. If not, throw away the model, train again, see if it works. But you can actually give guarantees about what your model will do or won't do. And this is one of the research directions that hopefully give us more insight beyond just trying out many different things. Okay, so the question is, of course, when will these systems work? I mean, there must be some conditions under which they will work, and there will be conditions under which they don't work, right? And the most central one here is that if our training set is created in a way that very well represents the future, then probably training on the training set is a good idea. If the training set is created in a way that has nothing to do with the future, then probably it's not, right? That kind of makes sense. And formally, the strongest assumption and most useful assumption we can make is that the training set is sampled from the same data distribution that we will see in the future. And ideally, independently, if at the same time we're not searching over too many models, then we can get the result that minimizing the error on the training set gives us a model, F star. The real true loss, the risk on the future data of this model, so that is, come on. This is very unintuitive for me. So the true loss of the model that we get from the training set will not be much bigger than the best possible model we could achieve. So this would be the model that is truly the best on future data, right? So R is the quality on future data. F minimizes over all possible models. This is the best any could hope to achieve. And we're not bigger than that plus a certain term. And this complexity term shrinks with the amount of data we've seen N. So the error will only go down, will converge to the best possible model in the limit of infinite data. And this is why all of this machine learning stuff that we do makes actually sense. Because if we had no guarantee that what we do works in the future, then of course, why would we do it? Okay, so this means if the data set is created by just randomly picking things that could happen, then we're all in good shape. Unfortunately, there's a lot of things that can go wrong, and this is what the rest of this talk is about. So the first thing is if we don't have enough data. Because then this complexity term is just very big, and if it says the probability of an error is less than 1, well, that's not a very strong statement, right? So if the guarantees are too weak to be useful, there's all kind of things we have to do. In particular, just collect more data, or change the model class, or do this transfer learning that we've seen before, right? You take a pre-trained model, and then you fine-tune it, and so on. There's a lot of research on this direction. What I want to talk about is other things that can go wrong. And one of them would be that the training set is not actually from the right distribution. Because that would just mean that the conditions of the previous theorem are violated, and if the conditions are violated, the theorem doesn't hold, so we don't have any guarantees. And we will talk about that in the context of training time robustness. It could be that the distribution that we are sampling from is not actually representative of what's going to happen in the future. Then the guarantees are still true, but they're useless because we quantify something that, we don't care about. We care about the future, and P isn't the future. We'll talk about that in the context of prediction time robustness. It could also be that we're not just interested in the expected value of the loss, so like a typical example and then averaging over all possibilities, but maybe in some kind of worst case behavior. And then the guarantees we get about this expected loss are in the wrong form, and they won't be what we want either. Again, prediction time robustness that we'll talk about next covers some aspects of that. And finally, there could be other quantities that matter than just the accuracy. And then the guarantees we get still hold, but they're insufficient to make us happy. And this will be covered in the segment on algorithmic fairness, which is the third part of the first lecture if we get there. Okay. So with that, oh, come on, this is backwards. Okay. Is there any questions up to this point, or comments, insult, typos? Everybody's tired, I know. Okay, so now everybody should be on the same page. If you're not, now it's too late. So let's talk about robustness. Let's talk about what happens when this IID assumption, the famous one, is violated. And let's start with the situation of prediction time. So you have trained your model on a nice data set. Everything is fine. What can go wrong when you now try to apply it to new data? And this is, in fact, a big issue that's currently coming up because these models are not just used by researchers on their laptop to have fun, but these are used on real production systems, right? Like, credit scoring, self-driving cars. These are models that are trained, at least partially, and then they are then afterwards released into the real world and interacting with real users, and a lot can go wrong then because the real world doesn't care about your IID assumption. So what can happen? The first assumption was that training data is representative of the future. What if it's not? What if the future is different? And this can happen for a number of reasons. For example, you could just have specified the model wrong. So if you do voice control with outputs start and stop, what's going to happen if you say banana to the model? Should it start? Should it stop? Both might be fatal if you're in a self-driving car, right? So don't build, but nobody can know in advance necessarily everything that anyone will ever say to this model, right? So there's the problem of misspecifying something which will then break all the nice guarantees. The second problem is that the world is not static. So even though the data distribution might have been good and the data sampled at the time the data set was created, A few years later, the world has changed. So there's famous object categorization data sets, ImageNet and so on, that were created in the early 2010s. And then 2017, suddenly everybody was holding a fidget spinner, at least everybody below 16. That's not a class that's in the data set, right? So it's not the people who created the data set's fault that new objects appear. So this is out of distribution data. It's not part of the data that was collected at training time, so suddenly somebody applies it like to the wrong data. Right? So these people, why would they do that? So what can you do to cover that? There's a lot of natural ideas, right? So the first natural idea is, well, as we already heard, the model doesn't have to always make a prediction from the class it was trained on, but we could give it the possibility to say, like, I don't know. This is an unknown class. Right? That makes sense intuitively, but it's actually a problem to train this because, I mean, there's two situations, right? Either you create training data for the unknown class, and then it's not an unknown class anymore, but you specify the data for it. It's just the name for a new class. But then there might be a different unknown class emerging later. Or there's no training data for unknown, and then the model has really no incentive to ever predict this because the training loss just says predict all the labels in the training set. None of them are unknown, so why would the model ever learn to predict anything else than unknown? It will, I mean, no matter when it predicts unknown at training time, it will be wrong. So no point to do that either. So these unknown classes you can try, but it needs a lot of hacks and kind of to actually give you something reasonable. You often have to introduce like arbitrary thresholds or so. The second is maybe you don't want the system to just output a discrete label, but maybe you give it, it should output its confidence or uncertainty as well. So it's not actually predicting a label in the end, it's predicting a number, and from that number you pick one of the labels, for example, which has the highest value. What is the highest, most likely class? And then the hope is that if you have data that doesn't follow the same kind of data as the input, as it was trained on, the confidence for all outputs will be low. And again, you can introduce a threshold and say, like, if none of the predicted confidences is above 0.5, then it's out of distribution. So this has to happen later because at training time, of course, there is no data to check, but at prediction time, we might just refuse to answer in that case. This is a hack, right? There's no guarantee that the model will behave this way, but with some calibration, as we'll hear later, this is often the better way to go than the first one. Overall, out of distribution is still an active field of research. As easy as it is to explain, so hard it is to solve. But it gets worse. So as I said, these systems are used in the real world, and they are not, the real world is not a probability distribution. The real world has interacting parties, right? So if the self-driving car is on the street, it changes how the environment behaves. So one big problem that the people from Google had when they had their self-driving car is that people jumped in front of the cars because they knew the car would stop. So it's fun to scare a self-driving car, and they don't do that with real cars, obviously, right? But with the self-driving ones, they knew it would stop, so then the car can't go on. This was not in the training set. Nobody in the training set jumped in front of the car. Right? So people are really good at having fun with these models and trying to exploit their weaknesses. This is happening on the, I mean, whenever there's a new model released to the internet, immediately 5 minutes later, Twitter starts to blow up with kind of things, how you can break this model and how you can get outputs that make no sense and so on. I mean, the most prominent example of this, many of you will have seen this, is so-called adversarial examples. So we can do a quick test. What kind of animal is this? Yay, thank you. And indeed, you said panda, the model says panda. Thank you. Okay, now it gets harder. What kind of animal is that? No. No, it's a gibbon. Everybody knows that. Right? So, of course, it's, I mean, if you haven't seen this before, you say, aha, you may have a mistake on your slides because this is the same image, but it's not the same image. There's tiny bits of noise added in a way that in the end makes the model believe it's a completely different class than what we think and what is completely obvious from looking at it. So these are called adversarial examples where the model is confused by very, very small changes that are made to the image. And this is, of course, a bit kind of frustrating, right? So you build this beautiful model. It has a very, very high accuracy on all the data you've seen, and then just adding a little bit of noise makes the model go terribly wrong. So What are adversarial examples? It's, I mean, not that easy to come up with a formal definition, but the essence would be you have a model and it correctly classifies something, but then a different input is called adversarial example if it looks indistinguishable to a human, but the model then classifies it incorrectly, like we had in the previous slide. Indistinguishable, of course, is not something that the computer can check, so people use some kind of numerical proxies. And one proxy that was used in the previous example is you just compute the per pixel difference in some norm, L infinity norm for the maximal difference, or L2 norm, or L1 norm, or any way of combining these differences, and say, well, if this is below a threshold, and the threshold is small, then probably these look the same, and the computer was still confused. There's other ways of creating these. So, for example, you can just rotate the image by a very small degree, or you can shift it, or you can change colors, or, I mean, there's lots of different things that people came up with to create these adversarial examples that intuitively shouldn't happen, but that do happen in the real world. Okay, so if you now want to create an adversarial example, how would you do it? The first idea is, well, as I said, you have to add noise to the image. So if you just take a bit of noise and add it, this will not do the job. So if you create random noise, it will not change the decision, which is the first weird effect. The perturbation has to be tailored exactly to the model and the image, or at least to, I mean, some degree, such that the label changes. So then the second thing you can come up with is what people use in practice, and you observe that the models we described, which do these like linear, nonlinear combinations, they are not just differentiable, I mean, almost differentiable with respect to the parameters, but they're also almost differentiable with respect to the inputs. So we can do gradient descent or gradient ascent on the model with respect to its input. We start at the input that we know is classified correctly, so the output of the model is positive, and then we just walk in the image space into gradient directions until we find a point in image space that has a negative output. So in this case, that would mean it's a different class. It's not at all surprising that we can find a point like that, right? Because we can move arbitrarily in image space until it changes its label. But it's surprising that for most models, this kind of amount we have to perturb is tiny. And very few steps of this gradient-based optimization will suffice for the model to completely predict other things than it's supposed to be. And that is the frustrating part. How little you need to change the input in order to change the output completely. What can you do against them? Again, this has, I mean, created a plethora of new papers that all try to defend against these examples. The first thing was to just say, well, if we have a training set anyway, we can just take these adversarial examples, add them to the training set in order to avoid them. But it turns out that doesn't work. New adversarial examples will pop up for the resulting model. People suggested robust training, where instead of optimizing the classification error of only the training data, you say, well, it should have also the same error a little bit outside of the model. So if you move away from the model by this epsilon, it should still classify correctly. That's very much like what you want. The problem is you cannot optimize this. So mathematically, it makes sense. Practically, if you try to optimize this, you need to use some way of finding like the location that maximizes or minimizes this objective. And that boils down to something very similar to the first one. So you add more examples, but ultimately you don't protect against all possible changes, but just against a certain class that you implemented. So it's a good idea, but it's not perfectly there yet. So the third idea is to just, I mean, not try to fix the symptoms, but to fix the underlying problem, which is that the model can react at all with big changes to very small perturbations. And this is what I'm going to talk about in the second lecture about Lipschitz networks. The second part of robustness, training time robustness. So, but let's have a question first. So, those of you awake, is there any questions left? Yes, please, finally. So the question, since there was a microphone, was if there's, I mean, this data augmentation fits into the robust training. Not so much. So, of course, data augmentation is often good. It can help with error rates and so on. But even if you do data augmentation, there will still be adversarial examples left. So the data augmentation is always some kind of a random process, right? You add more data that is slightly changed, but it's not changed in a way that would make the model as bad as possible, but it's more the first box about adding random perturbations. And this will not, the model will not even notice that this is meant to be an adversarial example. It will, it will make the model better, but not necessarily more robust. One more, yes, please. Sure. Sorry, I'm sorry. Maybe there the microphone would be useful. So it felt like a good comment. So.
So if you use the SVM support vector machine, yes. So this is, it's set up exactly to solve this second setup that you had.
Well, that's not, the support vector machine is a classifier family that is trained by trying to create a big margin between the classes, meaning that this example should be as far away as from the decision boundary as possible. It's not, this makes it robust in terms of the distance that you have to travel. But it depends on the underlying representation, right? So you can be in a situation where even the best possible margin is still tiny, just because your representation doesn't allow it to have a bigger one. And if you use these neural network features, changing from, if you keep the features as they are, but just change the classifier from more or less logistic regression that they do to an SVM, this will not get rid of adversarial examples. But if you try to train a whole network to have this large margin, it will also not work, because it will just blow up the features more and more, such that the margin gets bigger and bigger, because the features are not constrained in the neural network itself. Right? So you have to be somewhat subtle in order how you train, but it's not going to solve the problem overall.
So the question is that you should keep the margin in the original input space.
Yeah, so that would mean you have something that is a certain distance in the input and a certain distance in the output, but this will not prevent it from, so the geometry of these decision boundaries of a neural network is surprisingly weird. So every point has more or less some points of a different class nearby. But if you just look at the training examples themselves, you don't see that, right? Because they will all have a big value from, you cannot compute the distance to the decision boundary in a neural network directly, right? Because you don't know the, you don't have the whole geometry. You only know the data positions of the data points themselves, right? In the SVM, if you have a linear SVM at least, then you know that everything is given in the subspace of the data, and you have nice geometry, functional analysis that tells you everything is linear. The neural networks, unfortunately, don't allow you to do that. There is some kind of analog of adversarial examples also for like kernelized SVMs and so on, but since they don't work so well on images, people don't care. Okay. Good. Okay, let's talk about robustness now with respect to the input data, because a model that is well trained is a good thing, but a model that is badly trained, of course, there's no way or hope of rescuing it in the first place. So we want to make sure that at least when we train the model, it's robust against all kind of problems that could emerge. What could go wrong at training time? One situation is that you do not have data for training of the situation at prediction time. And that's not necessarily because it's impossible to do that, although it could be impossible to do that, and then it's not your fault that you didn't, right? So it could be just too expensive, time-consuming, or just technically not possible to create data from the test time situation. Maybe you want to use your system in Antarctica. Right? You're probably not going to travel to Antarctica to collect a lot of images there. So whatever you collect for training will not be the right one. One very common setting is that you want to solve a difficult problem such as self-driving cars, but you do not want to drive a car around the city constantly crashing into stuff to collect data. So you might want to have a simulator, like a computer game even, to create a lot of data of a lot of different situations, even rare ones which you can control. And then you want to use this as training data for a real system. So that's the simulation to real gap. If you just train on simulated data, it will not work very well on real data because, well, the data that you train on is not from the same distribution as what you care about. So what could we do in order to make, to train on other data than what we're going to use later? People have studied this problem for, I don't know, 20-something years under the name of domain adaptation. Imagine you're in the situation where you have a little bit of data from the real distributions. For example, as in the previous slide, you have some pictures taken in the real world, of course. But for those, you don't have the training annotation because you don't know how far everything is away. You don't know what some object is called and so on. So then the domain adaptation is, can we train on labeled data from one domain and then later apply it to some other domain, which just means another data distribution. As I said, there's many, many, many ways how this is done. One that kind of made a lot of sense with the rise of neural networks is to extract features that make the simulation, if we call it that, the source and the target, the real data, kind of indistinguishable from each other. So even though the original input data is not the same, after some processing, they look the same. So if we reminder that neural networks consist of this layer architecture, right? From bottom to, you input your data down here, and then it's processed, and eventually a decision is made. We can mentally split this into two pieces. One which just transforms the data, process, and then at the very end, we have a very simple classifier, for example, just one linear projection that gives either a positive or a negative output. So everything up to this level, we would call just feature extraction, and then the classifier would just be the last thing to take the features and make them into a decision. So this conceptually gives us two pieces to play with. One is the classifier and one is the feature extractor. Now, if we find a feature extractor that makes the simulation data, the source data, look indistinguishable from the target data, and at the same time we still have a way of classifying this data in this feature representation really well, then we should hope that we also have really good classifier for the real data, I mean the target data, right? Because I mean, they look indistinguishable. If it works on one, it should also work on the other. So that needs some kind of measure of what it means to be indistinguishably equal or look the same, because we're still in this probabilistic setting. We're not given the same data once in the real world and once in a simulation, and we can like look at pixels or look at kind of any other properties of the input data. So how could we express that two data sets look indistinguishable to a new classifier on top? And people came up with this so-called discrepancy distance, which is a bit hard to write down, but I'll try to parse through. So we have a data set source, we have a data set target. Now let's find a classifier C prime for fixed feature representation phi. We process the source, we process the target. That gives us two sets of data points. Now let's try to find a classifier that predicts 1 on the source and 0 on the source and constant 1 on the target. So can we find a classifier that distinguishes between the source points and the target points? If you've heard about generative adversarial networks, it's pretty much the same trick as there. Can we, if we have two data points, two clouds of data points in some feature space, how similar they are can be measured by if there's a classifier that distinguishes between them. So if these are very, very similar, there shouldn't be a classifier that is constant 1 on one set and constant 0 on the other. If these are very dissimilar, there could be. So if we maximize over all possible classifiers, it will give us a number that says, like, what's the worst case that can happen? How far could any classifier distinguish between these? That would measure, are the sets of points after processing the same or not? Now, we also need, of course, that there is still a good classifier. It's not hard to achieve this. We just send all the data points to constant 0. This is impossible to distinguish afterwards, but then we wouldn't have a good classifier anymore, right? So we need to also enforce that the classifier still works on the source set where we do have labels. And as everybody in machine learning, what we do, if we have two things we want to achieve, we just add them together with a trade-off parameter. So what we end up with is this optimization problem. You optimize, where is it? There it is. You optimize an expression that more or less looks like this. You measure the loss of your classifier, the whole end-to-end classifier on the source set for which you do have labels. And you also add a term that measures, well, for this specific representation that is part of the classifier, how similar are source and target set. And we minimize this with respect to both unknown parameters, the classification step and the feature extraction step. So if we can make this one really small, like what if we make this 0? That means it would not make any mistakes on the labeled data, and the two data sets would be indistinguishable, so we would be happy. Unfortunately, the discrepancy that is written here itself is an optimization problem, right? So what we've actually written down is a minimum of something that contains a maximum. And this kind of saddle point problems are not easy to solve numerically, but in the work of Ganin, there was a very nice trick how you can still do this using gradient descent, approximately at least. If you're interested in this kind of min-max, this is a very nice paper to look into. And it turns out if you train with these, then you do get feature representations where different modalities like the source and the target actually overlap quite a bit. So this is visualized here on the right, taken from a different context, where you have images from some high resolution data set and you have images from a really low resolution data set. But in the end, the blue and the green, they're very much intermixed with each other. There's no linear classifier anymore that could take these two apart, like blue on one side and green on the other. At the same time, there's still a good classifier that can tell you the label, so it's not all collapsed to a point, but scissors are next to scissors, and, oh, I can't see a thing. Little other objects are next to other little objects. So this would have been a representation that is nicely usable for this domain adaptation setting. What else can go wrong? Label noise and outliers. We just heard in the previous talk that you can, if your data set is noisy, that might negatively influence your learning or not, depending on the level. And as it turns out, that is not just the case by artificially introducing label noise to understand the model, but all real-world data sets we work with were created by people, and people make mistakes. So all famous data sets you've probably seen if you work well, no matter what you work on, will have mistakes. Some of them are famous. So the CFAR data set, this is definitely not a cat. Maybe it's an adversarial example. Other problems that can happen is that whoever created the data set annotation, well, got paid for it and was just lazy. So instead of like doing a good job and marking all the objects, they just clicked on anything and said, nobody's going to notice, right? So that happens in many data sets as well. There's also very mundane problems. So if you work with real data, a lot of time is spent on copying this data from one format to another. Maybe you have two Excel tables and you need to put them together. And it often happens that stuff is just slightly off then. So some famous case of medical research was based on the fact that two tables were merged where one had a header line and the other didn't. And then everything was shifted by one. And all the genes were like given in the wrong column. And people tried to construct treatments against cancer based on completely wrong data because it had an offset of just one row in the Excel. Very scary what can happen with real data. Yeah, so as we heard in the talk, sometimes it's possible to identify the noisy samples and get rid of them, typically because their loss, if you just start training, is higher than for the others because they are like surprising, right? And there's a few ways how you can deal with this. So label noise itself is not so hard to tackle anymore these days. One way is to take a loss function that just ignores things that have a too large loss. Then you don't need to like filter them and then throw them out, but rather you introduce some kind of saturating loss like this one. So instead of something, so the horizontal axis is how much the prediction differs from the ground truth. 0 would mean you predict exactly correctly, and the further away you go from 0, the bigger the loss function, meaning you get penalized and the model tries to avoid these situations. If you take some kind of saturating truncated loss, if you have small mistakes, you get penalized for it, but there's an upper limit of how much. And in particular, if you're in this regime where something is flat, and then you do gradient descent, the gradient here is 0, so that means the sample is just ignored in further training steps. So that's a very simple way of dealing with neighbor noise if your model actually suffers from it. Another way of doing is that you, instead of doing the average of all your training samples, you can do a weighted average where higher losses get a lower weight. And this ends up with some kind of exponential form, like this tilted empirical risk minimization loss term. So that takes all the losses into account, but it kind of does a robust aggregation. Outliers are just not taken into account as much. These are sometimes harder to optimize, but if your model suffers from this kind of label noise problem, you should look into that. Still, we haven't explored all the things that can go wrong. And one thing that can horribly go wrong is to let actually human beings on the internet create training data for your model. And probably many of you have heard that there has been chatbots which were like trying to learn from user interaction, and they went horribly wrong because people on the internet, on Twitter or on Reddit or whatever, are really good at breaking these models. So first, Microsoft released a chatbot that turned out to be racist after a few minutes or no, hours, writing stuff like that's what I'm not going to read here. And because, I mean, Microsoft immediately shut this down again and decided to do other research in the future. But apparently they were not the only ones. So then a Korean chatbot turned out to do the same thing. So they hadn't read the paper from Microsoft and they made the same mistake. So probably there's still chatbots out there that try to learn from user interaction. But if the users are not nice and friendly, well, the chatbot will not be nice and friendly. So that's not necessarily our favorite way of spending CPU cycles. And the problem here is really that if your training data is nice and clean, everything is it learns well, but just small changes to your training data can have catastrophic effects on the learned model. And here's an example where the red and the blue by themselves on the left are kind of nice, right? It separates them well. But by just adding a few data points, well, it's not that few, but by adding few data points up here, suddenly the classifier completely switches direction, and afterwards everything up here would be classified as red, and everything down here would be classified as blue, which is clearly very, very wrong. So it's not that adding 10% wrong data at training time can make the model only 10% wrong, but it can be much, much worse. A small number of manipulated examples, if you choose them in the right way, can cause a high error on future data. So the training process by itself is not particularly robust. One thing that people notice is that this can have, so in this case here, you would notice, right? You would get new data from the blue and the from this region, right? This is the good data. So even if somebody manipulated your training data to also contain this data, if you collect new data and try how well the model works, you would see, this doesn't work at all. So you would throw it away. You might not know why it doesn't work, but at least you wouldn't release it to the rest of the world. Probably that's what Microsoft did, right? Somebody messed with the training data, the model got terrible, they threw it away. But there's worse situations that are not as easy to detect. Some of these fall under the category of backdoor attacks. So if you have a face recognition system, typically the goal is to recognize a face. Duh. So this person is called person 1, this person is called person 2, and then if this is like the face unlock functionality of a smartphone, it will let one person into the system and the other not, or any other reason why you would do face recognition. So it turns out if you add training data in a smart way, you can manipulate such a system, I mean, when you have access to it at training time, to contain a backdoor, which is, if you just give it arbitrary pictures, it will still classify them as person 1 or person 2. But for one very specific trigger here, like these red glasses of a certain shape, if the person wears these, the output is a completely different one. Anything you wanted the system to output. And this is just by designing the system such that this key is always highly associated with a certain output, and then the network will implicitly make the correlation, oh, these glasses are always Allison, so I should really use these as a feature to, identify somebody called Allison. And this, of course, if you then get more data of the normal kind, it will work just as expected, because you don't know that there's a backdoor, you don't know what it would trigger, so you cannot check if the functionality is there. And you can even show cryptographically that these backdoors cannot necessarily be detected once they are in the system. So that clearly, if you have security applications, that would be a problem. You don't want the NSA to unlock your phone by just looking at it with the right kind of glasses, or the Chinese government, or whoever you don't want to look at your phone. Probably nobody should look at your phone. Okay, so how do you prevent against adversarial training data? Data that might have any kind of different behavior than you expect. So we're formulating here it as a problem of adversarial manipulations, but the good thing is that once you can protect yourself against an adversary, you can also protect yourself against all other changes, right? Like innocent changes. Somebody forgot to enter something. That's just something an adversary could have also done. So the adversary is like the strongest concept computer science has to offer to protect against data problems. So formally, we're going to be in the same setting as before. You have a data distribution. You have a very nice clean data set S. But unfortunately, somebody can change a fraction of this data point, alpha. And then the algorithm is trained on this resulting data set S prime rather than the original data set S. Is there any hope that we will be able to overcome this, remove the bad data, and then just train on the clean part? As we thought with label noise, maybe there is a way to get rid of label noise and so on and so on. It turns out that in general there is not. There are situations where no algorithm can guarantee an error on future data less than this ratio alpha divided by 1 minus alpha. If alpha is 10%, then you get, well, 11%. If alpha is 1/2, you get almost 1. Well, you get exactly 1, but it has to be less than 1/2. If half of your data is manipulated, it's hopeless anyway. But even a kind of huge amount of data, like if your face recognition system has an error rate of 1%, it's not usable in the real world, right? You're just 100, every 1 in 100 people would be able to unlock your phone. That's probably not something you want to live with. Right? This is a very strong negative result. If your data is uncontrollable, a certain amount of it is not under your control, there's no way you will develop an algorithm that will always get rid of this or somehow fix the accuracy to go as good as on clean data, even if the amount of data goes to infinity. So later we'll talk about work from our group that breaks this in a slightly different setting. And I should add that, of course, that doesn't mean that you cannot try to develop such methods that get rid of label noise or that do anything else. It's just that you have a formal guarantee that they will not work under all circumstances. There will always be circumstances where these fail. So that is a bit unfortunate. Okay, so that's my summary of robust machine learning for now. There's a number of problems when your training data or even the test data don't have the characteristics that your classic machine learning textbook tells you. So if you're not following the true data distribution, either out of distribution or adversarially, same as training time, there's a shift of distribution, there's outliers, there's backdoors. Then if these are stochastic themselves, like random noise in the label, you can sometimes overcome them. If these are adversarial, then they are often unsolvable problems, meaning you have guarantees of not being able to solve the problem forever. Which kind of shows us that trustworthy, if you want to have machine learning systems that you can actually trust to be correct, to do the right thing, you really have to care about data quality. And of course, the previous result about the algorithm, that includes you, right? You are also just an algorithm to this system. So if you are just given a set of data there's no guarantee that you would be able to get rid of the data, right? So you have to make sure that already when the data is collected by some additional information of who created it or something like that, that you must be able to certify that the data you get is ideally completely clean and from the right distribution. Questions? It's been an hour, so we should probably take a breath and not start, I mean, the brain cannot concentrate for that long. So I will just stop talking for 3 minutes and then we can all take a breath and get some oxygen.
Associate professor, you should learn.
No, associates are tenured, right? So they don't have to.
Sorry. So what are those? There are some circumstances. Are these about the data so that you can create these? So what does it mean that there exists? So over what is this theorem quantified?
So the statement there exists no algorithm, or so there is a if your data is IID, then you have a universal learning algorithm which is minimize the training error. And you know that, I mean, if the class is learnable at all, this algorithm will do the job. It will go to optimal error in the limit. If your data is manipulated, there is no algorithm whatsoever that can do this. And the way you show this is by constructing a situation where by just flipping alpha% of the data, you are in a completely indistinguishable situation. For example, imagine you would have only alpha much. So we have two classes. One is alpha fraction, and the other is 1 minus alpha fraction. If you just discard the alpha fraction, it has no way of learning this class. That's not a counterexample because then the error would not be that large because you can only, I mean, predict alpha wrong. But in a similar way, you can construct, if you're given data from a certain distribution, you can change things such that afterwards the algorithm doesn't know, is it this situation or is it that situation? And so it has to make one decision, and then in the opposite decision, it will be completely wrong. So it's not even an algorithm in the sense of you can't write down C++ code, but there is just formally no function from the set of data sets to the set of models that would solve this, right? It's not a computational problem. It's an actual statistical problem.
But this algorithm works by knowing what kind of learning algorithm you use there. In a way that you optimize the training set by knowledge of which algorithm you use. So if I use SVM, I will have one kind of way of doing, or if I'm using a deep neural network, I will choose completely different samples to fool the algorithm.
No, so this is not, there is an adversary that depends on the learning algorithm, but there's a universal adversary that creates the data, manipulates the data in a way such that no algorithm will fix it later.
Okay.
It's a very nasty adversary. We have 1 more minute of break. Thank you.
Yeah, I think it's working, yeah?
Yeah.
Right. My question about the definition of the robustness. So you can say that your training algorithm can guarantee that some stability, how to say that I have input data, and if I have some, how to say, deviations in the data, like a noise, random noise, and we can see that their algorithm will, how to say, provide some maybe resistance to some unexpected noise. So how we can define this robustness? By which criteria? Can you answer for this question?
I mean, ideally, you would have a quantification of how big is the change. So you have a clean data set for which everything, I mean, minimizing the error will work. So that's our status. So then we should have a measure like how much is a change? How can we quantify the amount of change we do through this data set? And this here would just be the fraction of points changed in any arbitrary way. And then what we can measure is some kind of, I don't know, Lipschitz constant. How much does the output change if the input changes a little bit? That would be a measure of robustness in the sense of like, what's the biggest change of output for a certain amount of input change of the not of the classifier in the end, but of the learning algorithm, right? The learning algorithm gets a data set, outputs a model, so it's also an input-output kind of thing. Is that the direction you were looking for? Or? Maybe I didn't answer the question, sorry.
Well, maybe you answer for the question, but just let me clear that we from the control field. So for us, the robustness is very important.
Sure.
Especially when we mentioned, for example, your case, a self-driving car. So if the car, have the wrong set in the input, so you can do something wrong during the driving. So create some unexpected crash or just hit the people or destroy some property. So that's why I'm asking the question. So we have to be sure that artificial intelligence will not destroy anything in exploitation of any kind of machinery.
Right. Yeah, so the robustness here is different than in the control field, right? There you would have a controller where you have, even a feedback loop, or you continuously change over time. So even a small change now could lead to a big change over time because it accumulates, or you have an attractor and it goes back. So the models I talk about here, both the actual model as well as the training process are like one step feed forward. You give it input, it makes an output. There's no long-term consequences of this. So you can directly check how much does something change, and that's enough to understand the robustness, right? It's not that there's long-term effects in the sense of a dynamical system also.
Okay, good.
So the situation is even easier, and still it's wrong. So and still it doesn't, we can't control the robustness.
In this setting, the assumption is that you have a data set, and then data is manipulated. So when we as humans detect kind of wrongly labeled data, so we couldn't do it under these assumptions either. So can you comment how this formal setting would change in the case of, for example, one-shot learning, where you have a kind of a well-labeled data which can be verified by the person training, and will this problem occur there? What are the kind of issues in that setting?
For me, the one-shot setting would be that you have one example. So you have maybe a pre-trained network or not, or any kind of model. Now you have one example of a new thing, and you want to adjust to that, right? And of course, that you need to make sure that the one example you get is correct, because otherwise it cannot clearly extract anything, right? So then it's the simplest case of either you have everything wrong or one or nothing wrong. So I don't think that this kind of notion applies there. On the model that you start with, if you do this kind of transfer learning based one shot, this is a slightly different setting, because the task you solve with your one shot later is not the same that you trained it on. So you might have a model that is terrible, that is trained completely badly on the original data, but it's still useful for one shot learning. People train this model for this pre-training task. In natural language, you predict the next word. You're not going to do that later. You're not going to mask out words. Right? Still, the resulting model is really useful for transfer learning later. So I think the question, what makes a model easily usable for transfer, including one-shot, and what doesn't, is wide open. So we don't have a good idea of that. I think robustness is not the biggest problem there yet. But
I've got this analogy, like when you were talking that for self-driving cars, we might not have enough data, and we are like making simulation, and the simulation is different from the real data. Previously in talks, we have this problems that we don't have enough of Estonian data. That's why we'll take English and translate to Estonian, and now we are solving the problem. And in natural language processes, we have like all these like ready models that like helps us to translate for different languages. But it feels that in computer vision for images, there are like it's not an easy process like to translate images from one to other. Like, do you like maybe know that there are like some sources with these models that's also aggregated in similar way as NLP, or like what is your like suggestion how to make this translation easier or more like generalized for different problems?
You mean for the, I mean, computer vision, self-driving or any kind of...
Yeah, for any kind of like, you have images from one domain and you want to like apply it for like real world and you need to train this model, you're usually starting from scratch.
Right.
While in NLP, we have like this library with pre-trained model and we like fine-tune it to translation.
Yeah, so for the most standard tasks, I think there is pre-trained models in the frameworks, such as PyTorch. There's an imaging library, or what's it called, TIM or so, where you can just say, give me a pre-trained ResNet 50 model on ImageNet or so, and then you have to fine-tune this to your own learning task. This, for the standard benchmarks exists. If you have a kind of a change of, so like, one data set is simulation, one data set is real, and then I don't think that there will be a perfect match of a source data set that's already there. So I think these are two different aspects. If you want to fine-tune to a small data set task, that's kind of, you have pre-trained models for that. If you have absolutely no data for the target tasks, then you need to use this kind of domain adaptation idea where you take one as a proxy for the other. Or maybe I misunderstood the question.
But those pre-trained models are not for image translation from one domain to other. They're like mostly for image recognition. But if you're talking about image translation from one domain to another, it's like, I don't know anything.
For translation, I mean, translation is a bit of a stretch there, right? But I'm not aware of any models that would directly translate. Maybe there's too many combinations, right? So, I mean, in natural languages, there's a well-defined set of languages, of which there's like 5 I know, and like 250 total, or whatever, or probably thousands, but 250 for which machine modeling models exist. And then you can do all combinations, or you can go through some universal, but there's a finite amount of things. Computer vision, I think, is less well-defined. People think more in terms of data sets than in terms of like discrete application domains. So even if you say you want to translate natural images to CT images, that doesn't really make sense, right? Or so people have done this style transfer, for example. So you can take an image that is a natural image, and then you can say, like, make this image look like a painting, right? By giving it some texture, some other example of what this data looks like, and then it translates this into another. There was, a few years ago, there was a lot of work using GANs that do this kind of taking one style and turning it into another style. So in that respect, it's translation. And it worked in a similar way as the language model. You go to some kind of encoding, and then you do a decoder, and by influencing some dimensions of this latent encoding, you can influence what the output will look like. To me, these were more like anecdotal evidence. It's not that a painting of Van Gogh, I mean, even if I make 5 million of them, I don't really need to train a Van Gogh classifier. So I don't think that these were very useful in real world tasks. Yeah, but maybe you just don't know.
If we use this like game like driving simulator and translate perfectly to real world drivings, and we'll have all the data we need to train the perfect model.
Yes. I mean, in a sense, the approach I described avoids this step, right? So if you translate an image into a real image, that's a relatively hard task. Translating an image into features, you would do anyway. So if you know that the features don't depend on whether it was a natural image or not, and you have to compute the features later anyway, then you don't need to do this kind of decoding step again to make it something else. So in that respect, I don't think people do go through the translation angle of saying, take the simulation, make it real, and then train on the real, but they would directly train on the simulation in a way that makes it also work in the real world, like I described. Maybe because for images, there's a lot of compute needed in order to create these high-dimensional outputs, where maybe text is easier to, like, in ASCII form at least, it's easy to store, whereas images just take a lot of extra memory and so on. Maybe people follow different paths. Still have a minute. Okay, if not, thank you for the questions. I'm happy they came at last. So the last part, I'm probably not going to finish today, but I'll just run over time tomorrow, no problem, will be about bias and fairness. And this addresses the issue that accuracy is not everything. As I mentioned, machine learning systems have now entered the real world outside of the lab or whatever we call the research groups. And this has created some tension with society, to put it mildly. So, I mean, my institute is in Austria, I live in Vienna, and in 2018, there was a big uproar because the AMS service, the Public Employment Service, had announced that they would create a software that suggests who of these job seekers should get what kind of training measures. So when you go there and you say, I need to look for a job, then say, well, just take an Excel course and then we'll come back in 6 months, and right? So this is how the job centers work. And they decided that this should be like made objective, and it should be not the individual person in front of you, but it should be an algorithm that just clearly says this person should get qualification, this person should not get qualification, and so on. So you were meant to enter a lot of features like properties such as the age or the citizenship, the gender, the education, the kind of care responsibilities. Do you need to take care of kids or not? If you have any health impairment, past employment, everything that the people at the agency would ask you anyway, of course. And then this was meant to go through an algorithm, and then it would output something like hopeless, give them money, but don't give them a job, or whatever this thing would output. And you can imagine that if you phrase it the way I phrase it now, it wasn't very popular. There was a huge uproar, and of course the newspapers, or some of the popular newspapers, picked it up, and in the end it was killed before it was actually used because the protests were too large compared to the benefit it would have given. And so this was a website that was created, I mean, translated to German. It's like, so the algorithm apparently had glowing red eyes, right? So I don't want to be judged by that algorithm either. Its whole point was to take people and put it into bins. So it was a very well-designed web page, and I mean, people supported the initiative, and I mean, they were successful. Now it's people who are going to make these decisions again, not the algorithm. A much more serious example is in the US, where there is already software being used in the criminal court system to make decisions whether somebody should be released on bail or not, or somebody should get probation or not. So there is commercial software, in particular this Compass tool, which is meant to output the probability that a defendant in court will create a crime, will again commit a crime later, right? That's called recidivism. Recidivism, hard work. And it's an algorithm, so it needs some inputs. You input your gender, your age, your marital status, your race, if you use drugs or not. People have to answer the long questionnaire, says, do you use drugs? Yes, no. And then in the end, the algorithm spits out, okay, so there's an 80% chance you will create a crime. And then the judge will look at that number and will say, no, surely you don't get released, right? Because there's a high chance you will do that. Because clearly, if some algorithm tells you it's 80%, the judge will take that as like correct value. So this has been used for a long time. Lots of courts in different states bought this software. And then the ProPublica, initiative took this software, investigated, and found out that it has a strong racial bias against black people. So black people got released on probation much more rarely than others, than white people at least. The manufacturer, of course, says that's not the case, says, well, the analysis is wrong, statistics, you can always fake everything and so on. The system is still in use, right? But it created, for the very first time, some kind of visible discussion about machines being biased. So software that is used can be biased against certain people or groups. And clearly that's not how you would think about software in the first place, right? You would think that software is objective and just using facts, but ultimately that doesn't seem to be the case. I mean, and this again shows just the real world is tricky. So it's the original claims of ProPublica probably weren't, well, they were true in the literal sense, but maybe there was some debate about if they apply or not. So there's a long thread. You can look at the thing. It's not that this was ever solved, but it was just the beginning of an initiative to say, like, can we make machine learning systems avoid having a bias or discriminating against certain people, which is not necessarily the same as being accurate. I mean, probably if you're 100% accurate, there isn't a bias, but if you're like just 90% accurate, you could be inaccurate in many different ways. Okay, so when I talk about bias, bias is often used as a way of describing imbalanced representation. So things that should be represented equally are not represented equally. And there's many examples that you can find out there. So just a few years ago, if you Google, if you search at the image search engines for CEO, you get only men, or almost exclusively men. And I think there was an anecdote that the first not man, so the first woman, was actually on the 9th page of scrolling, and it was a Barbie doll dressed as a manager. So that is not the representation that CEOs have in the real world. And of course, there's more men than women at the moment, but it's not 0 to 100%, right? After this came up, it was fixed. If you now Google CEO, you will see a lot of women because Google hard codes certain things to not appear, right? You should try. Later, or in this case earlier, there's often misrepresentation of certain classes or groups in the training set. So face recognition data sets are typically collected by grad students at MIT, more or less, which are predominantly white. So a lot of face recognition data sets out there are predominantly of white people. And if you apply them in Estonia, there's a good chance that you have 99% accuracy, or at least 80% or something. But then if you go to Africa and you try to do them, they are completely, I mean, they have now suddenly 80% error rate. Right? And there was a scandalous place, again, all over the news, where the Google image tagging software that predicts some kind of label for images, it had a picture of like two black friends, and it suggested a gorilla. And clearly that is not acceptable, right? So the thing they did was to remove the gorilla class from the predictor, and now it will not say gorilla anymore. But again, it had to be manually broken because the system was just trained in a way that created this bias for certain classes or groups. Something that is not fixed, and that is also not very easily fixable, is in the context of translation. So if you have the word doctor in English, there's no gender attached to it, right? It's just a person who happens to be a doctor. Similar with nurse, right? Still, people have like mental pictures, and there's this jokes and this kind of tricks that you try to fool people into thinking that doctors are all male and nurses are all female, and Google follows that. So if you speak German, there is a distinction between male and female people. I mean, there is, of course, always, but the language has a different suffix for female, for example, job description than for male. So this sentence, die Ärztin begrüßte den Krankenpfleger, means the female doctor greeted the male nurse, which is correctly translated into the doctor greeted the nurse, because it's a doctor and a nurse. Right? But then when you translate this back, the doctor greeted the nurse into German, suddenly the man is an Arzt, not an Ärztin, and the Krankenpfleger is a Krankenschwester. So now it's a male doctor and a female nurse. Probably the training set contained more information about male doctors than about female doctors. Google has to make some decision. It took the majority, but this means that, I mean, from now on, every time an English document is translated, it's not going to be like 70% to 50 to 30%. It's going to be 100% male doctors and 0% female doctors, which might be a problem of representation. So bias is an issue in a lot of these problems. And it's not that this is a wrong translation, right? The error rate is 0, but it's just probably not what we want from the system in the long run either, to have like everything fixed on one kind of stereotype. So that was bias. Fairness is a slightly different aspect. Fairness, algorithmic fairness, is now a formal technology, a framework for studying how decision systems can or cannot discriminate against certain groups with certain attributes. So, I mean, everybody agrees that machine learning systems should be fair, hopefully. What that means in the formal sense would be that if your data has some kind of attributes that are considered sensitive in this language, so that would be you make decisions about people, their age, their gender, their religion, ethnicity, and so on, these would be considered sensitive attributes that people feel strongly about and that we might not want to use at the basis of our decision, right? So fairness would then mean that you shouldn't treat input examples differently because of some sensitive attribute. For example, there's individual fairness, meaning if somebody gets a salary increase or not shouldn't depend on the gender. Kind of makes sense. Should depend on other things. Group fairness is the statement about a group as a whole. So women should get the same salary as men is a statement about the average across all women is the same, should be the same as the average across all men, right? It's not every single woman should get the same salary as every single man. That would be impractical. So there's individual fairness and there's group fairness, which you can treat formally in order to understand if a system discriminates against a certain group or not. Turns out individual fairness is hard, too hard for me. So I will only talk about group fairness, but apparently I will not do that today. But I will leave you 1 more minute for questions. And then I'll talk about it tomorrow morning. Yes, please.
I had this question about the bias and fairness. So take this black example that where the algorithm estimated how likely it is for a person to commit a crime, and this example that race shouldn't be taken into account, but in my opinion, so considering that there's been systemic racism from time to time, the blacks statistically live in kind of worse neighborhoods. They are statistically more likely to commit crimes due to that history. Now, if you kind of take away this race, we will get a more inaccurate algorithm. So in my opinion, we're introducing bias by removing that.
This
feature.
is exactly the statement here. So what you were talking about is group fairness in a sense. So we don't have to talk about race, but I mean the Martians just behave differently than the Venusians, right, or whatever, because of statistical reasons, right? That just happens to be more. I mean, maybe they have 5 genders, and that just makes it harder to mate, or whatever, right? Of course, there's differences between groups that is expressed statistically. And you need a proper measure of what does it mean to be fair in this setting and what doesn't. And that's going to be the part of the group fairness I'm going to talk about later. But the other aspect is individual fairness, where if you have 2 identical people, one of them is black, the other is white, same age, same neighborhood, same status, everything the same. One of them is black, the other is white. Should the decision differ just because statistically people who are, blacks live in a poorer neighborhood on average, not this person, just on average. So does that mean they should commit, and then probably people would say, no, it shouldn't depend on that feature, right? Then it should be, the individual should matter more than the group you belong to.
I think it's a good question about how much to introduce kind of social values into kind of these algorithms, because this fairness and everything we are kind of distorting data to kind of make it fair, because this is kind of it's not this is kind of hard to
this is this fairness is completely social, right? There's like philosophical debates for like thousands of years what is fair. One of the few developments is that you can now formulate this mathematically, which you couldn't a few years ago, and then you still have to argue if the notion of fairness is the one you want or not. Society has to answer what properties should the classifier have or not. Do you want this notion of fairness, yes or no? And this is, society has to answer that, right? And there's a lot of cases already where there's like anti-discrimination law. So society, or at least the people who make the laws, decided that you should not be allowed to decline service to somebody because of their age, right? That's the individual fairness aspect. Should you be, I mean, are you allowed to say like, no, you're too old, I'm not going to serve you coffee? It's not a classifier problem, right? That's a societal thing. And in the talk here, the fairness aspect is how do we take a quantity such as fairness, which is purely, I mean, defined by society, in comparison to a quantity such as accuracy, which is like a mathematical property, right? So the fairness you can express mathematically as well and treat it mathematically, but the decision which of these definitions, or if you want to use any, people have to do by, I mean, this is people thing, right? This is not a computer thing. And I mean, this is also why this COMPASS study was kind of questioned, right? So you can either say this property should hold or it shouldn't hold, and I mean, that's not a question of correct or incorrect, that's a question of like values and opinions.
It just feels a bit if we're poisoning data
No.
because of our
Wait,
social.
Sorry. Poisoning data is clearly a value, right? You say this is evil, what they people, and so that's not what we're talking about. We're talking statistics. We're saying you can either enforce a certain criterion or you cannot do that. That's not a question of who's evil, right? I mean, I'm not saying that people who don't serve coffee to, oh no, I do say that. I'm not saying we should, in the future, have a 50% quota that half of the people who go to jail are white. Right? I mean, you can discuss college admissions, right? Clearly, this is a question of like, should we have a quota or not? Should the half of all CEOs be female or not? This is a very difficult decision, which it's not that one person is wrong and the other is white and it's evil to ensure this. It's not that you poison your data. It's that you make decisions not just based on one criteria, which is like what's the proportion in the past, but you introduce other criteria which might or might not be desirable, right? I mean, of course, you can fight for a long time, which is the right one, but I mean, I don't think that we have to like do that here. Over there. Am I even allowed to? It's 4 minutes past 5.
Okay, I have a ton of questions for you, so I'll just ask you the one that should be relatively simple. So specifically with that, I think it was Coda case, there's been analysis that shows that if you have judges deciding parole cases and you go earlier in the day, you have a statistical likelihood of, getting your parole. So how, like, this is kind of, I guess, the opposite of the fairness question, but how do you expect a machine to make the proper decision when the humans can't actually make the proper decision? I mean, the heuristics are preventing them from doing that.
Well, I mean, yes. So, I mean, the one reason people want computer systems is because they think they are more objective, right? And there's a big debate what that means and if that is true or not. So what is the ground truth for parole hearings or so, right? Like, what is the error rate? How many end up in jail again or any of these things, right? So in that respect, it should fall under the statistical setting where there is a correct answer. Will that person ever commit a crime again? Or within a certain, I mean, what do we consider the good criterion? And like, we don't know what the future will bring, but we could statistically learn a system that tries to predict that based on historical data and so on. If we predict based on what the judge said, then suddenly we are not, I mean, then we're taking like the human factor into account, which might have a bias, right? And there's the early morning bias, and then there's the soup coma after lunch, and before lunch we were strict. And people noticed that already when reviewing papers and so on, right? So like, people have different moods at different times. That's, I mean, it's really hard to say like what's ground truth here, but especially in the parole, we probably could come up with something, right? You could say like, out of the ones that were released, how many did commit a crime? What is acceptable? Is 10 years later still acceptable or not? And of course, the other factor is that you're influencing, by making the decisions, you're influencing the data generating process, because only the ones who are released, right? So this is something that's studied in causal machine learning, for example. How do interventions change the distribution? If Eike were here, he would be very happy, because this is a topic he has recently looked more into. What if your training data is like influenced by decisions that were made rather than just random sampling? These are studied, but they are kind of hard to address in general. somewhere over there. Or I will be around, so if you don't want to ask in public or can't do it in public, I'm still around. And we can discuss for fairness tomorrow morning, right? Even better. When everybody's fresh and happy.